let's start with this conservation of angular momentum, all right? Example problem of point particle collision, okay? Now you have to understand, if you consider a system uh, with a bar here, right? And then the pivot point is right here, okay? And when these two particles collide at the end of these bars, it's gonna like have a like sort of like a war going on. Like this thing's gonna try to make it turn this way counterclockwise. This thing is gonna try to make it turn clockwise after the collision, right? So we have to see who's gonna win. Then just because this bar has a center of mass at the center of this geometric center, when these two actually collide, the center of mass will change on this. So if this bar is not fixed at this point to rotate, it would pivot around the center of mass somewhere along the bar after the collision. So it is very important to figure that out too. So let's read this and then see if we can actually get this started. So consider a system made up of 3 kilogram bar, right? 3 kilogram bar, 2 meters long, right? Initially at rest on a horizontal frictionless table. So it's frictionless table, so we're not going to have to worry about any kind of friction. Two point particle masses collide and stick to the bar after the collision. So this thing sticks to the end of this side, this thing sticks to the end of this side. A top-down view of the collision is shown. So this is bird's eye view, right? The bar is free to move. So it's not like fixed pivot point. It's free to move. So once they collide, it's going to start to turn, but as it spins, it may actually move translationally as so. Does that make sense? All right. The bar is free to move and it's not pinned at any point. So let M1 be 1 kilogram, traveling at 5 meters per second. M2 is 3 kilograms, traveling at 2 meters per second at 40-degree angle, as shown right here. So the bar looks like it has moment of inertia of just 1 kilogram meters per second, meter squared, right? So calculate the center of mass, okay, x sub cm of the system after the point particles stick to the bar. So you can treat the uniform bar as a point particle located at the center, okay? And mark x sub cm as a pivot point for the system on the figure, all right? So it looks like we can probably use, okay, the center of mass equation. So M1 is 1 kilogram. X1 is 0, because we're going to consider this to be our 0 origin right here. Plus M2, which happens to be 3 kilograms, times the bar is 2 meters long. So from here at the origin to where the M2 is going to be is 2 meters, right? So bar itself is 3 kilograms. And the location of the bar is halfway point of the 2 meter bar, so it's just 1. Whole thing divided by 1 plus 3 plus 3. I wish Doc would have made this different number. All right. So if you work it out, I think you get something like 0 plus 6 plus 3 is 9 over 10. So um, 9 over 7. I'm sorry, 9 over 7. So it's like 1.29 meters. That means my center of mass is going to be somewhere around here. My center of mass is going to be somewhere around here, right? And that would be my pivot point of the whole system after the collision, right? So this will be my pivot point. So it's going to rotate about at that center of mass point, and it's going to actually, right? So this is the H for the parallel axis. Because since it's not going to be rotating at the center of mass of the bar, you're going to have to use parallel axis theorem for okay. So using the parallel axis theorem, calculate the moment of inertia I of the system about the center of mass. Okay, so let's do that. First, we need to find the I bar, right, which is parallel with the center of mass. That is I sub Cm, right, plus m bar h squared. Okay, so we know I sub Cm for the bar is 1/12 m bar L squared plus m bar h squared. Okay, so here I think he already calculated us this I sub Cm for the bar, because if this is what 3 and then you get 2 squared, so you're going to get 4 times 3 is 12, so you're going to get 1. You see how you got that 1, right? So this here, whole thing here is 1, right? Plus 3 times 0.29 squared. So if you work this out, you're going to get 1.252 kilograms meters squared as your moment of inertia for the bar. Okay, but that's not the only thing we have, right? We also have these 2 point particles. So I sub Cm for the whole system is going to be I bar parallel plus I1 plus I2, right? So I bar, we know it as 1.252 plus M1 has MR squared, which is 1 times R happens to be from where we are right here, 0 to where that pivot point is. So my R happens to be 1.29 squared plus I2, which has mass of 3 kilograms, times the radius from this pivot point to where M2 is going to be, happens to be 0.71, right? 2 minus this, right? So 0.71. So if you add them all up, don't forget to square that. If you add them all up, you're going to get my I of center of mass of the total system, right? comes out to 4.428 kilograms meters squared. So this is the whole system's moment of inertia. Okay? This is I system. Okay? Or you could simply say I total. Okay? Or I told you so. All right? So this is what we have to use for the whole system. I'll put it up there. I'll leave it up there for a while so you guys can catch up and write things down. Now, we have find the total initial angular momentum, right, of the system just before the collision. Clearly, show work on individual particle calculation. I wish he would have given more room on this thing. This looks like. Okay, well, we'll work it out. So, how do we calculate the angular momentum for M1? Right? So, we can simply say angular momentum initial for 1, mass 1, right, is equal to R1 cross P1 initial, right? Now, you know that this is a cross product, right? So, if we were to look at R1, right, which happens to be 1.29 meters from here, right? So 1.29 times what is P? P is equal to just basically mass, right? So this is basically R times M1 V1 times, right, sine of, right, theta 1, right, n hat, right? That's what it is. So here we got R, M, which is 1, times V1, which is 5, right, times sine of, what is the angle of P and R? Is 90 degrees. And what about the direction? Well, if you look at the direction, so here's my R, right? And here's my P, right? If I were to redraw it, my R like this and my P like this. So what is that equal to? R cross P, right? So it looks like it's positive. R cross P is positive. So it's positive Z hat. Okay? Then, if we were to take a look at L, we should figure it out what that is actually. If we work this thing out, this is 1, right? So 5 times this. So I think you get something like 6.45 Z hat, positive, right? Z hat. Let's think about now L I of 2, which is R2 cross P2, which is equal to, right, R2 times M2 V2 times sine of theta 2. Now theta 2 is not 90 degrees, okay? n hat. So this comes out to R2 is 0.71 times M2, which is 3 kilograms, right? Times V2, which is 2 meters per second, times sine of, well, here's my R, here's my P, and the angle between that is basically 40 degrees, because the vertical angles are congruent, right? So this looks like 40 degrees. And R cross P, it looks like it's going into the page, therefore it's negative Z hat. So if you work that out, you will get negative, right, 2.738 Z hat as your angular momentum for second mass. Okay. Well, the bar itself was not moving in the beginning initially. So L bar is equal to 0 initially, right? Because that's not moving. So now we can say the total initial angular momentum is equal to, right? Simply L initial 1, right, plus L initial 2 plus L bar initial, right? So my total angular momentum initial is equal to then just positive 6.45 minus 2.738 plus 0. Right? So my total angular momentum initial comes out to positive, right, 3.712, right, kilograms meters squared per second Z hat is the total angular momentum before the collision. Okay, before the collision. So now they're asking, well, what's going to be the angular velocity? Angular velocity is really nothing more than omega, right? This is what we're looking for after the collision. We know, right, the sum of all initial angular momentum has to equal to the sum of all final angular momentum, right? So that has to be true, because angular momentum has to be conserved. We already know what initial total angular momentum is, right? We already know that this here happens to be, right, positive 3.712 Z hat, right? That has to equal to, this has to equal to I omega, right? So this I is the I for the whole system, which happens to be this that we already calculated, all right? So we can say 3.712 is equal to this I, which is 4.428 omega final. So what's my omega final? My omega final happens to be this divided by that, which should come out to positive 0.838 radians per second z hat. Because this is already positive z hat right here, so it came out positive z hat for my omega final. So that tells me my omega is positive z hat. How do you create positive z hat when this thing is spinning? Which way must this thing spin in order to create positive omega? Clockwise or counterclockwise? Clockwise? If it spins clockwise, my thumb is pointing in, so that's going to be negative z hat. So in order to produce positive z hat, it better spin counterclockwise. Is that okay? Right. So we can say it must spin counterclockwise. Okay. So it's most likely going to spin this way. Yeah. I mean, you could see who's going to win. Right? This one's going to win. So most likely. All right. Now that we know that they're going to stick on this bar and this thing's going to start spinning like this about this pivot point, but it's not going to stay there at one stationary point. It's going to actually rotate and it's going to move translationally because the thing is frictionless. Does that make sense? Right? Because it's not going to stay there. It's going to move translationally like so. So they want us to know, they want us to figure out what's going to be the linear velocity of this John. Now, it's going to be in two dimensions, so we better break this up into x and y components for this. All right? So we have to look at conservation of momentum linearly, how that's going to perform. All right? So here, let's think about going into let's do different colors for different things. I'm going to do like mass 1 as blue, okay? Mass 2 as pink, and mass bar as like purple, okay? I mean, you could try that. But bar's not going to have any initial linear momentum, right? So here, if I were to look at mass 1, right? So total momentum initial for mass 1 in the x direction is equal to m1 v1 x initial. But how much is this thing going in the x direction initially? Good, like you said, nothing, 0, right? Because it's only going in the negative y direction. So this is 0. Well, let's take a look at sum of all momentum of mass 1 in the y direction. That is simply m1 v1 y initial, right? And that looks like mass 1, which is 1 kilogram, times v1 is 5 meters per second, but it's in the negative y direction. So negative 5 meters per second y hat, right? So what is that, John? It looks like just negative 5, right? Y hat. So the initial total momentum for 1 is equal to just 0 x hat minus 5 y hat, right? Kilograms meters per second. Now let's take a look at the mass 2. Mass 2. So all the sum of all momentum for mass 2 in the x direction is equal to m2 v2x initial, right? That happens to be m2 is what? M2 is 3 kilograms, good, times v2x. Now, if this is 40 right here, my v2x is this, and this is also 40, right? So it's most likely going to be this times cosine of 40, so 2 cosine of 40, right, will give you my x component of my momentum, right? So this will be, I guess if you do this, 6 times cosine of 40 should give you something like 4.596 x hat. And then for sum of momentum for mass 2 and y is equal to basically the same thing but sine of 40, right? However, because it is going down this way, you better make that negative 40 degrees or 320, or just make it negative and then put sine of 40. Either way. So you could say negative 3 times 2 times sine of 40 degrees. Okay. So that is equal to the negative 3.857 y hat. All right. Well, guess what? The sum of all momentum, right? I could say sum of all momentum initial must equal to sum of all momentum final. Right? Sum of all momentum initial is if I add these two together, that's my initial. Right? So if I add this and this component together, I get 4.596 x hat. And then if I add these two together, minus 8.857 y hat as my initial. That has to equal to, right? This has to equal to the final momentum, which is m total times Vf. Does that make sense? Right? So if I have all this, we know what the mass total is. Mass total is basically 7. So here, 4.596 x hat minus 8.857 y hat is equal to 7 times Vf, because that's the 7 kilograms. So my Vf is equal to 4.596 over 7 x hat minus 8.857 over 7 y hat as my velocity. So if you want to, you can actually put this in digits. Just use your calculator. You should get positive 0.657 x hat minus 1.265 y hat meters per second as your total translational velocity of the system after the collision. Man, there should be more room. I'm going to have to tell Doc to make this into 2 pages. This is ridiculous. You know? This is ridiculous. Why did he shrink this all up like this? Into 1 page. I know he wants to save trees and stuff. You know, he's a tree hugger. But still, you know, for science, it's okay to have 1 more page, I think. I don't know. All right, so if you want to copy this down, you can. Now, obviously, the bar, I should have wrote down the moment for the bar, but you know it's 0 because the bar is not moving initially, right? It's not even turning, spinning, or it's not even moving. It's at rest. So the momentum for the bar is going to be 0. So I didn't even write that down. But if bar was moving, if it were moving, you need to have the, momentum for the bar as well. Okay. All right. All right. Letter F. Calculate the joules of work required to bring the system to rest. So once it starts to spin, right, and then move translationally. So you're going to have 2 forms of kinetic energy because as it spins, it's going to move. So you have rotational kinetic energy as well as translational kinetic energy, right? And if you want to bring that to rest, there has to be change in kinetic energy from final, which is 0, minus the initial kinetic energy of rotational and translational. That change in kinetic energy is equal to work to bring that to rest, right? So we know that work has to equal to change in kinetic energy, right? So the work is equal to kinetic energy final minus the kinetic energy initial. We know kinetic energy final has to be 0 because we're bringing it to rest. So the work that we have to put in has to be negative, right? 1/2 mv initial squared. Now this v initial is actually this v right here, right? After the collision. So this v and this v are the same v's. We have to find the magnitude of this, John. Plus, right? Negative, because don't forget, this is a negative for both kinetic energies. 1/2 I omega squared, right? So if you want, you could say negative kinetic energy rotational initial plus negative kinetic energy translational initial, right? So let's plug in some values. So we know that work now is equal to negative, right, 1/2 mass is the total mass, which is 7, right, times this. So what is that, John? We have to figure it out. What's the magnitude of this? So here we can say 0.657 squared plus 1.265 squared. And then you square root that, and you get 1.425. So my VF is equal to really my VI, which is equal to 1.425 meters per second. So here we can put that in here, 1.425 squared minus, I'm running out of room, so I'm going to put it down here, 1/2 I, which is that 4.428, right? .428, right? Times omega squared. What's my omega? Can we calculate omega? Right here. Omega final, right? And that is 0.828 squared. So if you work it out, your work comes out to negative this plus that, which comes out to 8.662 joules. So you would have to take out 8.662 joules of energy from the system to bring it to rest. Okay? All right, I'll put this up here so you guys can catch up on writing all this stuff down. Yeah, we need more room than this. This should be at least 2 pages. All right. Any questions? Right, it was okay, right? Understandable? Yeah, still wasn't that bad. All right, let's take a look at page 11. Conservation of angular momentum. Moment of inertia changes. Instead of having a constant moment of inertia, if you change the moment of inertia, because angular momentum is conserved, omega has to change. Right? Omega has. Anybody a figure skater here? No? Darn it. All right. Let's see if we could like provide some video demonstrations for people at home. Wow, wow, right? Come, child. I need you to volunteer. Come on. Have a seat. Can you guys see this at home? Yeah? All right. He's a brave soul. He's volunteering for this demonstration. Be like Jesus. I'm going to spin him around slowly. Bring it in. Whoa! Bring it in. Whoa. Right? Pretty cool, isn't it? Yeah. Right? Now what's happening here? He has point particles, right, outside. So his moment of inertia is mr squared times 2. He's got 2. Right? R is here to where that is. Now what he needs to do is he's bringing that in, changing his moment of inertia to his point particles, like very close to the center of axis. Well, when that thing decreases, because R decreases, conservation momentum says I omega. So if you're lowering the I, in order to compensate for that lower I, your omega has to go up. And that's exactly what's happening. There you go. I'm going to have to spin the other way so you can get undizzy. Bring it in. Whoa, whoa, right? So that's exactly what's happening. Now you may ask, wait a minute, didn't we sort of gain energy then? This kinetic energy just shut up. Did it? I mean, didn't it go faster? Where did this energy come from? Did we gain something new? I mean, like, think about that. Yeah? Well, guess what? He actually had to do work along the radius to bring that in close. The work he did converted it to kinetic energy, rotation. Great job. You could train for Olympics. Yeah, yeah. So as you can see, right, conservation of angular momentum will actually help the figure skaters, do this really cool stuff, right? Because if you think about like how these figure skaters, if you see them go in to that turn, I don't know if you were like figure skater or not, but I just love how like they come in. When they come in, they have like arms way stretched out, right? And one of the legs is even out, and then they come in. As they come in, they tuck in, right? They put the leg in, and they put the arms in really tight. Then you see them twirl really fast, and then they start doing this to figure, freak people out, and that's just conservation of angular momentum, you know. So let's talk about that more in detail, how that works out, right? So we already know the initial angular momentum has to equal to the final angular momentum, and it has to be constant, right? It has to be constant. And because the net torque is equal to 0, the dl has to be also 0. And that's why we have this, right? And since we know I omega initial, or I initial omega initial, must equal to I final omega final, here initial I is, so I initial is equal to 2 times mr squared. Now, obviously, you can't bring this weight set to Olympics. Right? You'd be cheating then, right? So I guess they could like sort of wear like heavy bracelets if they want to, just to. But heavier or more massive your hand is, more dramatic increase in spin you're going to get. So here we have 2m, and then this is r, right? R initial. Right? So 2 times mr squared is happening, right? Now, when the r is less, this is I final, okay? So let's say you decrease the r by half, but you probably do a lot less than that. I mean, if you think about it, you brought it in really close to your center of axis. So you're almost approaching 0 for your r, right? But let's just say you only do half as much, okay? Then what happens? Well, you get m 2 times m times 1/2 r squared, right? So what do you get? You get 2 times m times 1/4 r squared. So you get 1/2 mr squared, which is 4 times less, right? So here, R final is equal to 1/2 R initial, right? So you got 4 times, right? 4 times, I guess this should be R initial, because we substituted R final as 1/2 R initial, okay? Sorry for that confusion. So your I final, right, is equal to 1/4 the I initial, right? Because this is 2 times mr squared. This is 1/2 mr squared, so 4 times less. So in order to compensate for that, you're going to have higher omega, 4 times the omega, right? So if we continue that on here, right? If we continue that, my I initial, right, is equal to 2 mr squared, right, omega initial, right? And that has to equal to, right, 4 times 1/4 mr, no, I'm sorry, 1/2 mr squared times omega final. So notice how this cancels out with that, and bring the 1/2 to the other side by multiplying 2 to both sides. I get 4 times the initial angular velocity for my final angular velocity. So you'll increase your speed by 4 times. So imagine what would happen if he brings in like that's 1/10 of original radius. You could just already see how this thing will just blow up to like 100 times as original, right? But of course, he still has mass, or she still has mass for the center. You could consider that mass as like a cylinder, so that's like 1/2 mr squared, and that doesn't change, right? And also the mass itself is not as heavy, the hand itself is not that heavy, right? So you don't see like 10 times speed, but close enough, right? So that kinetic energy comes from the work that the skater does by bringing the mass in radially. That work done translates to changing kinetic energy. Okay, so that's how it works. All right. All right. Also, changing the moment of inertia too. So, all right. All right. Here's a crazy wabbit. So, Easter's coming and all, you're going to have Easter bunny in a playground. So, in a playground, merry-go-round, right, with mass m, so this has mass m, is at rest and is pivoted about a frictionless axis at the center. A disgruntled rabbit with mass m runs along a path tangential to the rim with initial velocity vi and bites into the rim of the merry-go-round, and it's going to be spun around in a circular motion, right? So once the rabbit bites this thing, it's going to be collision, right? Completely inelastic collision. In collisions, not only conservation of linear momentum has to exist, but conservation of angular momentum also has to exist. All right? So, what is the final angular velocity of merry-go-round disgruntled rabbit system? So, express the answers in terms of m, big M, r, and vi. All right. This seems rather like, oh my God, type of problem, but it's not. Why? Because we know the laws of conservation of angular momentum. That's why. Right? Initially, I only have the rabbit moving at VI. Merry-go-round is at rest. Right? So if you think about it, L rabbit plus L merry-go-round, right? But initially, this goes to 0, and that is equal to LF of mgr plus dr system. All right? Here, it is r cross p for the rabbit plus 0 is equal to, right, I both system, right, times omega final. What is the I system? I system is the disk plus, you could treat rabbit as the point particle, right? So you could say that this is the I disk, and then I rabbit is equal to mr squared. Does that make sense? So if you add them up, your I total is equal to 1/2 mr squared plus mr squared. So what's R? Well, R is just basically R, right? Times P is mass of the rabbit times V, initial, sine of 90 degrees, right, is equal to, here we have 1/2 mr squared plus mr squared times omega final. If we divide both sides by r, boom, boom, boom. Sine of 90 is 1. So we have mvi is equal to, right, 1/2 m plus m times omega final. All right. Therefore, I forgot my r somewhere. Let's factor out the r. Yeah. So if we solve for omega final, then here we have m times v initial, divide that by r times 1/2 m plus m as my omega final. Well, we know the mass of the rabbit is not going to change unless it loses a couple teeth, right? Merry-go-round's not going to change. The mass is that going to stay this constant. And r, the radius of this merry-go-round, is not going to change. So these are all constants. So you can see this omega directly depends on how fast this rabbit runs before the collision. So they're directly proportional to one another. Okay? So omega final is directly proportional to mv. Okay? Or I could just simply say v, right? Because m is also constant. So this is the answer that we're looking for. Okay? All right. So be careful of those disgruntled rabbits in the playground. All right. Disk colliding with disk. This is sort of like, I don't know if you drive a stick shift. When you hold the clutch in, this separates, and then you switch gears, and then you release the clutch, then it engages into the disc to make this transmission turn with the engine, right? And that's basically what it is. This is like a collision with disks, okay? So this is the initial condition, and this is the final condition, okay? So top disk, it's disk with a moment of inertia I1 is rotating with angular velocity of omega 1, right? So this is omega 1, about a frictionless shaft. So there's no friction here. Right? It drops onto another disk with moment of inertia 2 at rest. So I1, and then this is I2 initial, omega 1, and this is 0. Because surface friction, the two disks eventually attain common angular velocity. So this is omega final, basically. What is it? Again, we have to just start with the conservation of angular momentum. Initially, I have I1 omega 1 initial plus I2 omega 2 initial is equal to I1 plus I2 omega final. We know that this omega 2 initial is 0, so this whole term just drops out. And omega initial 1 is just omega 1. So I1 omega 1, right, is equal to, right, I1 plus I2 omega final. Right? So here, my omega final is equal to I1 omega 1 over I1 plus I2. Now notice the direction of my omega final. It has to be same direction as my omega initial, okay? Because this is the only one that's indicating which way it's going to turn. All these i's are constants, okay? So both disks omega must have same direction, right? So both disks right, must have same omega and same direction, okay? Omega final, right, depends on, right, how much of the total inertia is from disk 1. Okay, so the final omega pretty much depends on how much this original disk had, right? I mean, that's kind of obvious. Right? That's kind of obvious. Are you okay with that? Yeah? Let's do one more. Let's do one more. Let's do one more. 15 minutes? Okay, we can do it. So here we go. Conservation of energy, right? Forces and torques. Okay. So consider a system shown to the right here. Mass M1 and mass M2, which is the disk right here, are solid uniform cylinders. So I is equal to 1/2 mr squared. Okay. So this is a solid disk, and mass M1 is being pulled to the right by its axle and is rolling without slipping. So this is rolling, which means it has rotational motion as well as translational motion. So this has two forms of energy when it's moving as this thing falls. This one only is going to roll, I mean, not roll, this is only going to spin, so it's only going to have rotational kinetic energy as this thing falls. This one starts with potential energy initial, and that will convert this into kinetic energy of the whole system. So beginning, you only have potential energy of this M3. As this M3 falls to here, right, it picks up speed, and as it falls to H, this will have translational kinetic energy, this will have rotational kinetic energy, and this will have rotational and translational kinetic energy after it falls H. Does that make sense? Right? Okay. So that's good to know. So let M1 be 2 kilograms. So this is 2 kilograms. R1 is 0.1. M2 is 1 kilogram. And R2 is 0.2 meters. M3 is just 5 kilograms. All right. So we can start by using conservation of energy to calculate the speed of M3 as it reaches down here. Okay? So let's think about there's no work done by friction because static friction, right, that allows rolling without slipping does not generate heat or reduce energy of the system. So I think I mentioned this earlier. The static friction to make this object roll does not contribute to work done by friction, remember? Right? It's good to know. Okay? So since we don't have any work done by friction, because nothing is sliding, all right, we can simply say that. So initially, right, everything starts from rest, so I have no kinetic energy for any of these three objects. I only have potential energy, gravitation, by mass 3. It's the only energy I start with. Then, for total energy final, after this thing has fallen this much, I have kinetic energy rotation for mass 1 final, plus kinetic energy translation, right? 1 final, plus kinetic energy rotation of mass 2 final, plus kinetic energy of mass 3 final. Right? This whole thing right here is kinetic energy final for the whole system. Okay? It's good to know that because these masses are pretty much connected with this string, as long as the string does not stretch or shrink, when this has this speed, this has to have the exact same speed. And the tangential velocity of this pulley has to be the same as the translational velocity of all objects. Okay, so let's put that down there too. It's good to know. The string, right, will keep all these the same, as long as it doesn't stretch or shrink. Okay, and that's very, very important thing to know because it helps a lot. Right? So the V for M1, V for M2, tangential, and V for M3 has to be the same because of that string. Okay? So as long as there's no slipping, right, we can say V sub Cm for mass 1 has to equal to V tangential of mass 1, which is equal to omega 1 R1, which is equal to V tangential of mass 2, which is equal to V3, and they're all basically V's. Okay? So since they're all same V's, we can just drop the subscripts and just use V as a common V for every one of them. That makes it more convenient, I think. All right? So now we can go back to this. So now we can say, okay, M3GH must equal to, this one is 1/2, right, times I1 omega 1 squared plus this one is 1/2 M1 V squared plus this one is 1/2 I omega 2 squared, or I2 omega 2 squared, right? Plus 1/2 M3V squared. Well, these omegas can be replaced with V over R, right? And I's can be replaced with 1/2 MR squares. So here I have M3GH is equal to 1/2 times 1/2 M1 R1 squared times here V squared over R1 squared. So notice what happens to my R1s, right? Plus 1/2 M1 V squared plus 1/2 times 1/2 M2 R2 squared times V squared over R2 squared plus 1/2 M3V squared. Whew. Now we can sort of cancel out this and this and this. So what do we have? So I have M3GH is equal to, this looks like 1/4 M1V squared plus 1/2 M1V squared. So this looks like 3/4 M1V squared. Here I have 1/4 m2v squared plus 1/2 m3v squared. Now we can plug in some values. M3, 5 kilograms. G, 9.8. H, 0.245, right? Is equal to 3/4 times M1, which is 2 kilograms, right? Let's factor out the V's, V squares, right? Plus 1/4 M2, which is 1 kilograms, plus 1/2 times M3, which is 5, V squared. All right? So if you add all these up, on this side, you're going to get 4.25 V squared. Multiply all this out, and I think you get something like 12 joules. So your V is equal to square root of, 12 divided by 4.25, which comes out to 1.68 meters per second. Okay? Check my math, just in case. All right. I don't think I have time to do the next page, which has to do with same thing, but we're going to use forces to do the next page, forces and torque. Okay, but I'm not going to even start that right now because it's going to take a while. So I'll stop it here for today, and we should be finishing along. So you need to start working on your homework problems as much as you can. Okay, and then we'll finish up by Thursday for chapter 12. I know chapter 12, 11, 12 assessments coming up soon, so you have plenty of time to work on it, guarantee it. All right, so I'll stop the lecture here.